In part D, we're up to 19 milliliters of the added hydroxide. If we look at our graph at point D, okay, we're getting close to, well, we're getting close to the upstart, okay? We haven't hit the the full up. We've gone past the whole buffer zone and we're ready to do this problem here. So at 19 milliliters, all right, start the problem exactly the same way, filling in an ICF table, putting moles into the table because the one-way reaction goes to completion, not to equilibrium. The value for the moles of HA, we keep on using the same number because that is not changing, 0.00498. To get the moles of the hydroxide, we know it comes from the moles of the sodium hydroxide. So we take the molarity, that's moles per liter, times the liters, which is 0.019, okay? And that's going to give me the moles of the sodium hydroxide, which is getting pretty close, but not quite as big as our starting amount of the weak acid. So I will put it here, 0.00473. Again, we're assuming that this hasn't happened yet, so we don't have any of this yet, and we have the water. We look at these two numbers and we know it's going to go to completion until it consumes the smaller. That's the smaller. So it's going to consume all of this and leave me with nothing. But the change line is taking place here according to the balanced equation. So 0.00473 goes here and adding 0.00473 to that number. So now I've got the amount of the amount of conjugate base left over. Let's see how much of the acid is left over. When I do this subtraction, I have another 0 in there and a 2,5. We still have a significant amount of a weak acid and its conjugate base present in solution. We still have an ability to use the Henderson-Hasselbalch equation. pH equals pKa, which is the negative log of the 1.54 times 10 to the minus 5, plus the log of the moles of the base, 0.00473, and the moles of the acid. So once again, we have more base than acid, so expect this value to climb here. The negative log of this number we have seen already in a couple of our problems. I actually did multiply this out here and got 1.277, and that is going to give me a value of 6.089. I could probably only know this value actually to 2 decimal places, which means I'm starting to lose my ability to know this quite so well. That would probably be a better answer for my pH value without the extra significant figures. But we see that it's climbing. We also see, if we're looking at this graph, where we are in point D is we're getting ready to leave that buffer zone. All right, we could maybe consider it to be that area there and still be able to use the Henderson-Hasselbalch equation. But if I went on and did part E, I would still have a similar situation in which I had some acid and some base present. But the values are such that we no longer can use the assumptions that the Henderson-Hasselbalch equation uses. So you couldn't, we'll say NaOH equation. You couldn't use that there. And I am not going to show you that. We've got to not have assumptions, and we're going to have to use the quadratic. But this is how you do it up until you're no longer at the buffer zone. And I will tell you, for this class, you won't have to go in that little space on either side of the equivalence point.